The next speaker is Professor TsuyoshiYoneda from University of Tokyo. The title of his talk is Vortex Stretching and Enhanced Dissipation for the Incompressible 3D Navier-Stokes Equations. So please.
Thank you. Thank you very much for inviting me this opportunity to talk in this nice conference. Today, I'd like to talk about vortex stretching and enhanced dissipation for the incompressible 3D Navier-Stokes equation. And first, I'd like to explain the background. I'm now working on the turbulence and especially statistically stationary developed turbulence. In this study field, they want to figure out a concrete picture of the energy cascade dynamics. And in this field, there is some classical result on the we call Coulomb-Gorff law. This is the cornerstone of the study of the energy cascade. And in this cascade, they assume Zeroth law. I will explain later. Zeroth law is significantly assumed. And the plan of this talk is first, I would like to derive the Coulomb-Gorff law briefly because I think not so many people know about this 4-5 law, so I explain about it briefly. And after that, I'd like to explain the recent turbulent physics result in 3D Navier-Stokes turbulence by DNS. And after that, I would like to propose a sophisticated cascade picture based on such recent turbulence physics results. And this is a joint work with Professor Goto, Oka, and Tsuruhashi. It's still in preparation, but yeah, the result is now we made something. And this is not typo. Why? Alphabetically, I have to go the last, but this paper is some physics paper. We are trying to make some physics paper. So in this case, we need to designate some first author, and it's me. So this is why the Y, Yoneda, comes into the front. And in this result, I'd like to explain the derivation of the Coulomb-Gorff's 5-third law. And I'd like to also derive this famous norm, L3 Bezoff 3 infinity 1/3 is equivalent to the epsilon. This epsilon means energy dissipation rate. And this norm is in Konstantin E. Titi's paper, 1994, very famous norm. And last, I'd like to derive the Zeroth law. And this is a pure mathematics result done by In-ji Jeon, who is now in KIAS in Korea, published in this year, 2020. And yeah, we derived the Zeroth law from a vortex stretching formation. And based on some breakthrough result by, we use some breakthrough result by Lagrangan Lee, published in 2015, and Kiselev-Shivrak, published in 2014. Okay, anyway, first I explain the derivation of the Coulomb-Gorff 4-5 law. And okay, this is a Navier-Stokes equation. Maybe everybody knows. And here we put some external force here in some wavelengths. We put some K force, okay, K sub force. We put some external force. And we get, as usual, we get energy balance, this energy balance. And this is due to the fact that this skew symmetricity, if U is smooth. Okay, in this talk, we always assume Navier-Stokes equation, assume always smooth. And Zeroth law, I explained the Zeroth law. This is the starting point of this talk. Under the normalization of this initial data, the mean energy dissipation rate does not vanish as nu to 0. So this value do not tends to 0, tends to some number we call epsilon, energy dissipation rate. And where this bracket means some ensemble and long time averages, And this is well known rather in physics. Laboratory experiments and the numerical simulations of turbulence both confirm this above Zeroth law. But actually, we do not need to consider we do not need to use the limit function of this u nu. Okay. And stationary. So we consider stationary turbulence. So even, okay, if we take average for the here, time derivative should be 0 because stationary turbulence. So which means we just apply Zeroth law here. Then this external force term becomes epsilon if we take nu sufficiently small. And the following calculation on the 4-5 law is based on the famous book Frisch. I think this book is very good for mathematicians. Very interesting book. So I recommend you to read Frisch's book to learn turbulence. First, we decompose the velocity field U into mean and fluctuating parts. So, okay, we take coarse graining in ball. Ball means we take, okay, first we take Fourier transform and cut off on the ball with the radius, the order 2 with the power k, capital K, and take back to the real space, take inverse Fourier transform. This is we call coarse graining in ball. And then we get some Navier-Stokes equation, just calculate. Then the point is that this stress tensor appears, tau k, we call stress tensor. This is stress tensor. And we would like to get some energy balance formula. So we multiply this u bar k and integrate on both sides. Then we obtain this energy balance formula. And, stress tensor, we have stress tensor. So stress tensor turns into the energy flux. This is we call energy flux term. Okay. So this is the point. And okay, we already got this external force term is equivalent to this epsilon. So we can get this energy flux term is also epsilon. Okay, because this term, if we take a time average, this term becomes 0, and this term also becomes 0 because this already cut off onto some frequency. So if we take nu to very small, then this term also becomes to very small. And this is epsilon, always epsilon. So epsilon equal this energy flux term. So we finally got this formula. And then in physics, we call scale by scale energy transfer across the scale 1 over k. This k means k is a wavelength. So 1 over k is some length scale. Anyway, we got this formula. And from this formula, we extract some third order velocity correlation tensors, something from this energy flux, and take limit appropriately. Then finally, we got the Coulomb-Golf's 4-5 law. But we need, okay, this is very important. We need to assume some homogeneity and isotropy. So turbulence means some flow, literally homogeneity and isotropy behavior. So if we assume this both of two, then we finally get this formula. And what's this? S is a third order velocity structure function. This is a structure function. And okay, anyway, this is mathematically, this is nothing more than Helder. It tells us that this is a Helder 1/3. Okay, so we have here R, and yeah, this is expressive Helder 1/3. And this is the same as the Onsager's conjecture. They are saying that singularity appears, Helder 1/3 singularity appears in some dispersive Euler flow. So this is the same conclusion. So let me express the recent result in turbulent physics. And recent physics, usually they use DNS, which is direct numerical simulation, which means directly they solve Navier-Stokes equation, 3D Navier-Stokes equation by using a supercomputer. And I think this Goto Saito Kawahara is one of the breakthrough on this Navier-Stokes turbulence study field. And they calculated the Navier-Stokes equation in some periodic domain. Reynolds number is all very high, 100,000, and the resolution is 1024 cube. And their conclusion is that the main mechanism of this kind of Navier-Stokes turbulence is that vortex tubes tend to align in the direction perpendicular to the large-scale vortex tubes. So you see, this red expresses large-scale vortex tubes, and yellow is smaller than this red vortex tubes. So you see, so vortex tubes tend to align in the direction perpendicular, literally perpendicular to this larger scale vortex tubes. And this is due to the fact that the vortex stretching effect. Because by Biot-Savart law, larger scale vortex tubes create strain tensor. So strain tensor stretches the smaller scale vortex tubes, then it creates some, stronger vortex tubes. And I'd like to one more result. Recently, Harvard group, they showed the similar result done by McKeown, Ostila, Monico, Brenier, Rubinstein. Let's watch. Okay, first let's watch their movie. They post some movie on their published journal. Wait. So, okay. Let's go to the first. So they calculated DNS, vortex tubes, and instability occurs. Then all of a sudden, secondary filaments form between the such vortex tubes, vortex cores. Then neighboring filaments counter-rotate and interact. This secondary filament counter-rotate, interact, and this is very interesting. A new iteration of tertiary filament forms during such breakdown, perpendicular to the both secondary filaments and dissipation. Okay, so this is published in this year, and they are also saying that almost the same result as the Goto Saito Kawahara's result. Very interesting movie. And moreover, supports of vortex doing stretching and stretching vortex done by this joint. Okay, please keep in mind this disjointness. Okay, this joint, and this is two scales interaction. You can easily see two scales interaction and compressing or stretching. And we say, okay, coherent eddy. Okay, please keep in mind this joint, two scales interaction, compressing, stretching. Then I'd like to give a new result done by me and Professor Goto. Goto is the same as Goto Saito Kawahara's Goto, and Oka and Tsuruhashi. And the key idea, different from a classical theory such as the fourth law, is to distinguish the turbulent regions into two parts, occupied by such coherent eddies or statistically independent. Okay, this is a new idea. And okay, first I recall the 3D incompressible vorticity equations. Okay, this is just usual vorticity equations. And the same as the fourth law, we decompose the vorticity and velocity into mean and fluctuating parts. But the different thing is that we take coarse graining in annulus, not on the ball. Okay, we take Fourier transform and cut off on the annulus, then take Fourier inverse to go back to the real space. And we plug, we plug U bar k into the usual this vortice equation and multiply U bar and integrate on both sides. And divide it by this k with power 2 square. This is, we need this adjustment to adjust to the energy dimension because this is vorticity. So we need to adjust to the energy dimension. So dimensionally correct to, this is dimensionally correct to get the energy. So we get this energy balance. And the point is that we have a vortex stretching term here. Okay, omega dot nabla u k dot nabla dot omega k. And by the same calculation as the 4/5 law case, for any epsilon star strictly very smaller than epsilon, there is some k dissipation. Okay, this is this k this. This is funny. We already use the epsilon as the energy dissipation rate. This is in physics, we always use this epsilon as the energy dissipation rate, and we already use this epsilon. So we need to use a different notation. Yeah, and in mathematics, we would like to use epsilon as very small, but I had no choice. So we use different notation, epsilon star as the epsilon delta definition of limit. So this epsilon star expresses some smallness. Anyway, such that we get this vortex stretching term becomes very small because we are taking annulus as the coarse graining. And we give now decomposition to extract such intensive vorticity or vortex filaments. So for any fixed t, then we decompose the vorticity, something like this, by using h and d, parameter h and d. And this capital Wj is some representative vortex filaments and scaling by capital K. Wk is smooth and some sprimum and L2 and L3 norm is nearly equal to 1. And the disjoint, okay? Each representative vorticity, vortex filament is disjoint. And we choose this Wj and H. H expresses some Helder exponent. To attain the maximum value of this capital D, this expresses the number of intensive vortices with a restriction. Okay, this R expresses some remainder term. So we need to control remainder term with some constant gamma for some fixed gamma. Okay, rigorously, of course, this is a fixed time t. So rigorously, we need to take some time average to get this H and D. Okay, we give some picture. Okay, so we have intensive vorticity. For fixed t, we have some intensive vorticity, vortex filaments, something like this. And we pick these vortex filaments up and numbering W1k, W2k, WK with power dk. So we have k with power d elements in this picture. And if k becomes smaller, so picture becomes something like this. Okay. Yes, and we can take this capital D because W bar k itself could be WK. So the worst, we can take D. The worst number D is 0. Anyway, we can take some number D. Then we decompose the vortex stretching term. Choose an intensive vorticity, WJK, and fix it. And if there is a vortex stretching or compressing relation between these vortex filaments and some other intense vortex in this scale, 1 over k with power k prime scale, then we pick this vortex up. Then we denote omega 2 with the power k prime capital Kj for such region. Okay, this is the first step. Okay, first we choose some vortex stretching relation or compressing relation. And the second, pick all of such relation up for all capital K. So we take every scale to pick all such relation, vortex stretching or compressing relation for all scale. The other regions we regard statistically independent, and these become 0 if we take ensemble average. So this is why we call coherent eddy scenario. And the gradient of velocity induced by an intensive vorticity is appropriately denoted by, because we are just looking at intensive vorticity, so it suffices to take a Biot-Savart law to the intensive vorticity. Okay? Then we denote U by U with the power k prime, capital Kj. So anyway, we have vortex stretching term. And first, we take little Perry decomposition to the both omega and u, little Perry decomposition. Then we extract such a coherent eddy. Okay, we pick all of coherent eddy up for the fixed this capital Wjk. And as I said, supports of vortex doing stretching and stretched vortex done by it are disjoint as a movie. So this is approximation, but I think reasonable. So this vorticity, only this Wjk itself survive here. Everything due to the disjointness, everything, almost all vorticities die. So only itself survive. And here we look into scale interaction by stretching and compressing. Okay, so we come here and here the same function. So we put the same function here and look into the interaction. We don't know what it is. So we need to look into here, strain tensor. And here we need to employ some direct numerical simulation. And this is a very beautiful simulation. We could get very beautiful graph, something like this. This is a numerical simulation on capital F K prime, okay, in inertial range. We are not taking time averaging. This is a snapshot. Even snapshots, we get very beautiful graph. So you see, we have a positive bump here, and we also have negative bump here. That's it. Very beautiful. So in inertial range, for fixed capital K, this function fk prime is decaying function in k prime. Okay. Yeah, this graph should become something like this. So decaying function here, clearly decaying, with one positive bump and one negative bump. And the shape is self-similar. So here, one positive bump and one negative bump. Yes. And this is why I think we can approximate this capital K prime to some positive bump and a negative bump. So we just pick some two elements. The other one should be small, so we just pick two elements. Okay. And near the forcing scale, this line, we don't need to care about this line because this line is due to the driving force, so we don't care. So the point is, near the forcing scale, we only have negative bump here. Okay. And okay, let's go to the next. So we do some significant approximation with a scale locality. We approximate that this one positive bump is capturing just one scale stretching compressing as a movie, not multi-scale. So we have this approximation. So yeah, go back to. We have a summation here, K prime. So we in mathematics we have a lot of terms, but due to only two bumps, so we can approximate only two functions. Okay. And I think this approximation may be valid and unavoidable due to some uncertainty principle, because you remember that for the decomposition, we use a compactly supported function for the intensive vorticity, but we are taking Fourier transform and Fourier inverse transform, and it means that this uncertainty principle should be unavoidable. So we need to consider a lot more about it. But anyway, we can approximate. And taking sum in J, then so finally we get this vortex stretching term becomes this formula. Okay. K alpha, K some alpha is less than 1, bigger than 0, some number. So 1.7, 0.58. So alpha is 0.58 or something, 0.5 or something. Okay. Alpha is 0.5 or something. And alpha inverse here, K alpha inverse K. And recall that this term is already small. So we have this formula. Epsilon star expresses smallness. And here we have to employ some physics, vortex stretching and compressing, rather well known in physics. The case in this nabla U bar alpha K, larger scale strain case, in this case, the effect of strain compared with compression is dominant. More precisely, some non-intensive vorticities are stretched by this nabla U bar alpha K, that is aligned with the eigenvector of the rate of strain tensor nabla U bar alpha K of the first positive eigenvalue. We denote this positive eigenvalue as lambda K, tilde is a typo, K plus. This is a positive number. In other words, we have this formula, omega bar K dot nabla U bar alpha K is nearly equal to lambda plus alpha K omega bar K. Okay, because aligned to some first positive eigenvalue. In the case, on the other hand, this nabla U bar alpha inverse K, smaller scale strain case, is that the effect of compression compared with stretching by smaller scale eddies are dominant. That is by some negative value lambda, okay, we write lambda minus alpha inverse k negative value. Then we can approximate it by this one. Omega bar k dot nabla u bar alpha minus 1k nearly equal lambda minus alpha inverse k omega k. Yeah. The larger scale vortex tubes disappear due to the compression effect by the small scale vortex filaments. And this scenario is related to the, in Harvard group paper, they emphasize this elliptical instability. So I think due to the elliptical instability, compression effect occurs, then, yeah, energy transfer. So this is the picture. So if lambda plus is positive, then this is stretching, literally stretching. And if lambda minus is negative, compressing. Okay. And we can evaluate this eigenvalue, lambda plus minus k. This is estimated by the intensive vorticities due to the scale locality. Please remember the movie. So stretching vorticities and stretched vorticities are close to each other. So this is why we can estimate the eigenvalue by using intensive vorticities. Then we get this lambda k plus is k with the power minus h plus 1, and lambda minus k is estimated by minus here, minus k minus h plus 1. Okay. Anyway, so what can we get? We give some example by using AJ, some positive real number sequence. Initially, driving force F creates the large scale eddy. Sorry, here typo. So A1 should be equal to epsilon. And the next A2j minus A2j plus 1 equal to 0. This is done due to this formula. Okay. We consider some sequence. So AJ is one of this one. AJ is one of this one. So we already showed that A2j minus A2j plus 1 equal to 0. This is done. And still not think is AJ minus 1 minus A2j equal to 0. We would like to show this one, still not. But once we showed this one, then we got that AJ is always epsilon. This is what we want to get. And one more difficulty, still not part. We say local energy transfer formula. So we have to show that this combination, K alpha K K plus here, alpha K K alpha K. This combination also should be small. And this formula is in good agreement with recent results, physics result by Motorori Goto sensei. This is a very fresh result to appear in JFM. And also Doan, Soina-san, Davidson, and Tanahashi, 2018. By using their physics results, then we can say that this formula is good agreement with such recent results. But for more rigorous proof, we need more mathematics, and I think, to be honest, I think I have no time to explain about this part. But this part is more, for me, it's more interesting, and I'd like to explain in the future, and a bit more complicated. But more or less, we can give some more rigorous proof about this local energy transfer formula. Anyway, once we got this local energy transfer formula, we get this AJ equal to epsilon formula, which is epsilon is this one block. Epsilon is nearly equal to this one block. And this one block is nearly equal. Minus 1 over k square with mean value lambda k and L2 norm of W k with power 2. Okay? Then, anyway, we got this is very happy. We got the energy dissipation formula by using, recall that H is a Helder exponent and the D is intermittency exponent. So we finally got the energy dissipation formula by using Helder exponent H and intermittency exponent D, capital D. This is we are very happy. Up to now, but up to now we cannot say anything about this intermittency exponent D by math calculation. This is our future challenging work. And by experiment, it is widely observed that D is nearly equal to 2.8. Anyway, we got this energy dissipation formula. Once we got this formula, we can derive the Coulomb-Gorov's minus 5/3 law. And the energy spectrum, okay, energy spectrum is defined this minus k with power minus 3 and L2 norm of W omega k with power 2. Dimensionally correct. This is dimensionally correct. And by using this energy dissipation formula, and this is easy math calculation. We easily get this 5/3 law. And one more interesting thing. How about L3 norm? This is based on L2 norm. So we take L3 norm. Then H and D disappears. Helder exponent and intermittency exponent disappears in this L3 norm. In other words, this is the same norm. Just we take L3 Bezoff norm B3 infinity 1/3. This is equivalent to this epsilon, energy dissipation epsilon. And this is, as I said, this norm is famous and you can find in famous paper, Konstantin E. Titti's paper, 1994 paper. Okay, so we already derived Coulomb-Gorov 5/3 law. So let us switch to the Zeroth law analysis. This is more pure mathematics. We only use pure mathematics. Consider now 3D Navier-Stokes flow, no forcing in a periodic domain. Okay. And okay, I say first the main theorem, Zeroth law in a fixed time interval. This is done by Inji Jeon and me, published in 2020 this year. There exists some absolute constant delta such that the following statement holds. For any A0 bar in between 0 and 1, there exists a sequence of C infinity smooth initial data, omega n 0, parameter is n, with uniform bounds in L2 norm. And viscosity constant mu n tends to 0, such that the unique smooth solution un nu n of the 3D Navier-Stokes equation with initial data un 0 and viscosity satisfies this lower bound. Okay. Yeah. So the point is we can take A0 bar we can take A0 bar to close to the 1 as you want. Okay. Then we get this lower bound formula, and this is nothing more than the Zeroth law. Of course, we have this modified term, but as I said, we can take as you want close to 1, so almost Zeroth law. And remark, we need to construct this theorem, we need vortex stretching to show this theorem. Okay, so now explain the equation. We consider 2 plus 1/2 dimensional Navier-Stokes Euler equations. So, okay, this is vorticity equations. And we set some large scale, small scale vorticity. And 2 plus 1/2 dimensional solution we consider. So here, okay, one component, 2 variables. Here, 2 component, 2 variables. And once we set this initial vorticity, then we can decompose the vorticity equation into 2 equations. One is just 2D Navier-Stokes Euler equations, and the other one is just transport equations. We can decouple into 2 equations. The most important thing is to construct the initial data. So from now on, I explain the initial data. So we consider in here, so parameter, this is a bit complicated. We consider the periodic length. We parameterize the periodic length by capital L, which represents the scale of the large scale vorticity. Okay. So this is the initial data. And the largest, and we some cutoff by small l parameter. Also with some smoothing modifier. This is not so important, but just we say smoothing Buffet-Sherman solution. This is okay. If we don't have this cutoff, we say Buffet-Sherman solution. So this we call smoothing Buffet-Sherman solution. And the small scale vorticity. Okay, we put simply this one. And the important thing is that this D prime region. Okay. I explain later, but okay, first we show the picture of the initial data. So for the smoothing Buffet-Sherman +1, +1, -1, -1, we have here +1, +1, -1, -1 in periodic box, but already parameterizing this periodic length by capital L. And we put small scale vorticity here in this region, D prime. I explain later here. So this strain, so this Buffet-Sherman smoothed Buffet-Sherman solution creates this strain field. Then this small scale vorticities are stretched by this Buffet-Sherman smoothing solution. And now let us focus on this region, D delta. So we have here Buffet-Sherman smoothed solution. Length scale is capital L. And here room scale is small l. First, we have a ball here. The scale is L. And as time goes on in delta, then this Buffet-Sherman solution boundary shape becomes some boundary moves, waving. So we pick a smaller rectangle inside this solution. Okay. Then we consider the strain field. Then we'd like to pick up the region near the origin where the strain affects stronger. So this D becomes smaller ball rather than smaller ball than this initial time ball. Okay. But in delta time, in this D, stretching is working. constantly. Here, D, we denote L tilde, okay? We put some factor L bar C delta. Delta, it's natural to appear this delta because we first solve the 2D Euler equation, Navier-Stokes equation in delta time. So we got a small region D, and the parameter is L tilde. We say L tilde. And we pick this D up, and we would like to consider the stretching effect to the smaller scale vorticity. So in delta time, this smaller scale vorticity should stay in this D in delta time. Okay? Should stay in, not go out. Must not go out. Should stay in this delta time. So we need to take smaller and smaller ball to stay in delta time. So we pick some D prime region here. Okay, we put one more L bar C delta to this L tilde. So this is stretching small scale. So we pick this smaller scale stretching region. Okay, this is some preparation. Then we just calculation. The key idea is the key idea is in this picture. Every key idea is in this picture. Once you got the main point, then just calculation. The lemma, sharp lower upper bound of the strain. Let omega be a unique solution to the 2D Euler equation with initial data, large scale initial data. Then we define the velocity field U L. Then there exists constancy such that for any delta. And in this D region, we get this lower bound. But the point is that we can estimate lower bound of this strain, D1, U1. Okay? And the sketch of the proof we give, just explain briefly. To get this lower bound, we just apply Kiselev-Shverax breakthrough result. They use some geometric lemma to find a region where the vorticity is not small in the fixed time interval. Just use a 2D structure since the vorticity is frozen onto the Lagrangian flow. Okay, so first we pick some region. Then we apply L infinity unboundedness of the singular integral. Then some logarithmic term naturally appears here. Some logarithmic term appears here. And upper bound is more some classical. Go back to the Kato's result by 1986. Just use a logarithmic Sobolev inequality. So we can get the upper bound also. Then the second lemma, creation of large Lagrangian deformation. Okay, for this D prime, then we get this almost the same lower bound and upper bound for this Lagrangian deformation. The key formula is just Lagrangian ODE. Here we have this ODE. Then just calculate. The third one, since this small scale, just that this is a transport equation for the small scale vorticity. So we get this formula. And in this solution formula, we already have here some Lagrangian deformation part here. So we plug this Lagrangian deformation formula onto here. Then we get some lower bound of this formula. Epsilon, this script epsilon, I explain later. Then we get some sharp lower bound for the Navier-Stokes we want to show. This is the Euler part. So what I want to show is for the Navier-Stokes case. Okay, this is Navier-Stokes solution. It should be controlled by this Euler solution. In order to get this formula, we need some implicit limit. So Euler solution minus Navier-Stokes solution, we estimate it in L2 norm. And we can do by very careful calculation. I have no time, but just calculation. Each step is rather elementary. Just apply some Sobolev inequality or some Herder inequality or something. But finally, we got very complicated formula, something like this. And the epsilon, script epsilon is here. Okay. And this determines, here we, of course, we have nu here. So this determines the maximum value of nu, viscosity nu, this formula. Okay. And one more calculation we need to do, because to consider the zeroth law, we need nu. We put here nu with power A0 bar and estimate again to get a lower bound. And carefully we consider the balance of, in this case, we carefully consider the balance of all parameters, in this case, including A0 bar, and each norm depending on various length scales. I already explained 4 length scale variables, capital L, L tilde, and L bar. So just consider balance estimate, then we get the result. Thank you.
Thank you, Professor Yoneda. Do you have any questions or comment? Okay, so Professor Terasawa, please.
Could you show the result about zeroth law?
Yes. Yes.
So in that slide you mentioned, so it is you do not know A0 bar can be taken to be equal to 1. Right.
Here further works.
Yeah.
Yes.
That's what I wanted to ask about. You mentioned it.
Yes. This is yes, and to tell the truth, I also working on this with Inji.
Okay.
Yeah, and maybe we can say something about A0 bar equal 1 case.
Okay, but so there are some difficulty.
Yes, of course. But we can say recently we did something, and
okay, thank you.
Yeah.
Are there other comments or questions? Okay, I have one question related to the Professor Terasawa's question.
Yes.
So which part is difficult in your proof to choose A0 equal to 1?
Difficult. Yes. We need upper bound. Okay. For the estimate, we need upper bound and lower bound. Okay.
Okay.
So, yeah, this is very delicate estimate because if lower bound is too strong, then we cannot get a good upper bound. If we get a too good upper bound, we cannot get a good lower bound.
Okay, so when A0 equal to 1, this estimate does not hold. You cannot get a nice estimate like this.
Yes. In this strategy, we cannot get such a zero. Yeah, we cannot get.
Okay, thank
Yeah,
you.
yeah.
Are there other questions or comment? Okay, if not, thank you, Professor Yoneda, for your nice talk.